In this wrap-up video for potential dividers, we're going to look at a couple of circuits and make sure we really understand what the LDR is doing. Let's start with circuits like this. If the surroundings are bright, the light is dim. And as the surroundings get darker, the lamp brightens up. I'm going to switch to just thinking about potential differences, so let's swap to a voltmeter. We know that if the resistance of the LDR is high, the potential difference across it will be high. So let's plot a graph of brightness against resistance for an LDR. It starts high, then curves off as light intensity increases. For this circuit then, as the light brightness increases, the measured voltage decreases. How about here? How does the room brightness affect the measured voltage? Notice how the voltmeter is now placed across a fixed resistor? Have a think. Well, the trick here is that the measured voltage does not depend on the resistance it is placed across, which is what you might be thinking. If measured voltage does not depend on the resistance it's placed across, what does it depend on? How should it be phrased? What language should I be using to describe it? So, measured voltage depends on the share of the resistance it is placed across. When the light is bright, the 10 ohm resistor has a large share of the total resistance from this equation. So the measured voltage is large. But when it is dark, the 10 ohm resistor has a small share of the total resistance, so the measured voltage is small. This short video is here to round off our work on potential dividers. If you followed along okay, then you're probably fine. You're probably ready for the next part, where we're going to be looking at logic circuits, where we can really start to expand on the capabilities of these wonderful little circuits.